Hi, everyone. So, welcome to the second session of the homomorphic encryption. In the previous session, I just had a brief introduction about what is homomorphic encryption and what are the applications that we mainly saw in healthcare or in finance and many other places that we can use this type of encryption, especially when we don't trust the server that is processing our data. So now in this session, I'm gonna dig a bit deeper into that. We go gradually towards the implementations. Also, we don't have the implementation itself in the sessions, but we'll talk about some considerations that are very important and pave the ways for the future conversations. I hope also maybe I bring this and it helps better so you see my screen too. So again, we're gonna talk about like how to get from the theory to the production environment. I'm gonna show you later on that you can actually start doing this right now on your environment and in your company as well. So when it comes to the life cycle, there are a couple of considerations that we care about. One of them is the scheme selections. For example, what are you using? There are a couple of algorithms or a scheme that you have to have in mind. The three famous ones are BGV, BFE, and CKKS. I'll have more conversation around each of them later on. And specifically, I'm going to talk more about CKKS. And the reason is that it has a lot of applications for AI and so we first of all choose the scheme. Second, we have to choose our parameters. Like, are you looking for the security that is equivalent to AES 128 or AES 256? Uh, I mean, not necessarily AES when I say I'm just saying like what is the key length that you're looking for. And then we have the encoding, like you have to map the data into polynomial representations that I showed you a bit about it in the previous sessions. When you do this mapping, the next step is to do the computations that you apply some gates to your data to perform the encryption. That was the learning with error problems that we saw. And then we have the decryptions that we are recovering the final results that is done by the client. So when to use BGV or BFE? These schemes are very nice for exact arithmetic on integers. So if you don't want to have an error, and if you're working on integers, these schemes are really nice. So if, for example, if you're doing a database query or if you are counting the votes or any task where you don't want to have a rounding error, this is the right technique to use. For example, for counting votes, you cannot have some rounding errors, or for database, if you make an error, you end up in a different row. And that is not what you wanted to search for. Also, between BGV and BFE, BGV is faster for the deep circuits that you have like a higher amount of operations, but BFE is easier to parameterize, especially for those of you who are beginners to the field. And finally, the king here of the whole, that is CKKS, is a standard industry standard for AI and is more for machine learning and is actually working with floating point. For example, CKKS treats the noise as a part of the decimal precision. Instead of 5, you might get like 5.00000001, which is okay because it's gonna reduce the accuracy of your model a little bit, but it's not really the end of the world. Because let's say instead of 99.9% of accuracy, if you got 99.85, still that's a great accuracy, so there's no really problem. So again, choose between CKAS or BGV, BFE. It all depends like, is it okay to have rounding error or not? If it's not okay, go with BGV or BFE. If it's okay, then you can use CKKS. The other term that is very important in homomorphic encryption is called the context. But what is a context? It's basically like an engine room, which means that it holds all the encryption parameters. It's basically just like a rule set that tells you what are the polynomial modulus degree that you have, coefficients that you have, what is the scale factor that you're using in your equation. So it's kind of like store all those important information for encryption because the both the client and the server needs to know that parameters. And the server needs to know those rules, otherwise server cannot do the decryption. I mean, not don't need to do the decryption, but server cannot even do the operation on the encrypted data. And consistency, if there is a mismatch in the context between the client and server, that can create a failure later on when the client decrypts the data, which is also problematic. So public keys can be shared from the client to the server because server needs that too. And secret keys, of course, gonna be stayed only with the client. And the gallows key, or what we call a helper key, that's technically like an encrypted key here, needs to be shared with the server. This helper key doesn't really allow the server to decrypt the data, but it allows the server to do some computation on the data. Later, when we get to the specific scheme, we'll talk more about it. And what about the hardware barriers and acceleration? So you see, like the current CPUs that we are using are mainly built for 64-bit mathematics. And that's mainly the servers that the computer that you're using. And homomorphic encryption routinely requires here thousands bit integers. So that's much bigger. How are we gonna solve this problem? And also there is a memory bottleneck, like moving massive ciphertext from RAM to the CPU causes what is called a data starvation, which means that the CPU needs to keep waiting for the data that slow down the homomorphic operation. GPU is actually one way that we can solve this problem. GPU, like in CUDA approach, can create at least 10 times the speed up, or even maybe up to 100 the speed up, if you have optimized GPU kernels that are optimized for lattice-based mathematics. So also you can do a lot of parallelization. Let's say if you have 1,000 pixels and each of them takes 1 second, for the operation that would be 1,000 seconds. But if you do all in parallel, that takes you only 1 second. So you're saving 1,000 second, and you just do it in 1 second, which is very nice. And ASIC is the other that you talked about it. This is the like application specific chips that you can use. There are a lot of great companies like Kornami or Chain Reaction that are building some chips that you can reconfigure and do parallel processing that are really nice for fully homomorphic encryptions. And also we have energy efficiency because if we know that we need to do bootstrapping to get rid of the errors or error cleaning process. And these are like using a fraction of power that is required by a server farm. So instead of using a normal CPU or GPU that you're using for other applications, it is much faster to use an application-specific chip or maybe even FPGA. So FPGA actually is an easy way to do that because instead of buying and spending lots of money on fabricating a silicon chip, you can buy an FPGA and you can redesign that circuit that you like. And there are many firms actually right now using FPGA as the homomorphic encryption accelerators. If under data centers today. What is the difference between multi-party computations and homomorphic encryptions? So homomorphic encryption is not the only way that you can do this privacy preserving computations. Also, there are other techniques that we need to talk about. One of them is MPC, or multi-party computation, which means that data is split between multiple parties and no single server will ever hold enough information to reconstruct the entire original data. So it's like we have a data, we split it, we share it between multiple servers, and now each of them has a piece of that. So this is much faster than homomorphic encryptions because we are using a standard arithmetic, not like those polynomials that we use in lattice space. But also it requires constant talking between the servers because each of them has a piece of data. So if the internet connection is down, then the entire computation is stopped and we have to restart it, which can be inconvenient too. So here, if you are working on and dealing with cloud outsourcing, which we want to uh, give all your computation to be done on the cloud, in that case, use homomorphic encryption. But if you want to do collaboration, use MPC or multi-party computations. Here, of course, the computation is is fast in the MPC, but the communication is also takes a lot of time. And in homomorphic encryption is actually the opposite. It means that the computation is slow, but communication is fast. We have one other approach that is called trusted execution environment, like Intel, SGX, and AWS Nitro is just to create a physically isolated computation zone. Basically, this is like a virtual machine. And the data is decrypted inside this black box. So the cloud owner cannot really inspect the access, but only that chip or can see the data. So the process that is really fast, and there's no penalty for heavy cryptography stuff. But there is one bottleneck and one problem in cons, and that is the fact that you have to trust the manufacturer. And if there is a backdoor or if there is any side channel attack on the hardware, then the privacy is gone. So have that in mind. So it's not really a perfect solution anyway. So if we compare this two for trusted environment and homomorphic encryption, so in the trusted environment, you have to trust the hardware, but in the homomorphic encryption, you don't need to trust the hardware. You just need to trust the mathematics. And if hardware is compromised in the TEE, the data will be exposed, but here the data still is safe in homomorphic encryptions. Performance is very fast in TEE, but in HE is very slow. When it comes to flexibility, you can run any code on the TEE, but in HE, you just can do algebraic operations. You need to trust the cloud in TEE, but you don't need to trust the cloud in HE. And side channel, the risk is very high in TE, but it's very low in HE. And TE has been already used in production, and HE is more something emerging concept. And the cost of TE is low, but the HE is high, especially for computation cost. Just to have some type of problem that are hard for homomorphic encryption. One of them is like, if you want to compare is A is greater than B, which is a very simple operation for your computer, it's actually very hard for homomorphic encryption in the homomorphic encryption landscape because this is a nonlinear logic, and we cannot do nonlinear stuff. Instead, we have you remember the last session also I talked about it, that you have to use Taylor series for approximating the some activation function, right? ReLU that you are using in neural networks. The same here, we have to approximate that. So we can use sign function to estimate this comparison, which of course gonna add noise, but we have to be careful to manage that noise properly. So again, when you have nonlinear operation, those are very hard for the homomorphic encryption landscape. Instead, you have to convert them to a form that homomorphic encryption can understand and can work with it properly. So here we have it again. Are you using the homomorphic encryption for inference or using that for training in AI? Inference means that you already have a pre-trained AI model and you just provide the encrypted data and the model runs on it and then tells you what is the result. This is very easy quite easy for homomorphic encryption. But the other one that is even more complicated is in training. Let's say you want to train a model uh, using encrypted data. So your entire database is encrypted. This is very nice. Imagine you could do that actually because the model then wouldn't learn about the data itself. But the problem is then you have tons of or millions of multiplication during the backpropagation of neural networks. So is it really like a tsunami that gonna absorb like all the power computation that you have? So this is a very big challenge. If we can solve it, of course, we solve a lot of problems in AI security too. And I talked about data expansion already in the previous sessions, which means that if you have again 1 MB of CSV file, when you do the homomorphic encryption on it, that can become 100 megabytes. So that's much bigger. Or in the worst case, that can be even 1 GB of data. You see so much expansion of the data. And that can be a problem for network, especially if your network is slow. The other thing to have in mind is the integer wraparound. Like if you are, we have some coefficients, and if those coefficients become very big, since we are using modulus, they will actually wraps around zero. It's exactly like a clock. That if you get to 11, sorry, this clock is very distorted. And so if you get to 11, next time you get to 12, and the clock resets. So the same happens here because we're working with the modulus. So you have to be careful because sometimes if we do this type of mistake, and then if we might get the wrong result if an wrapping happens and we don't take that into account, we get the result that is very inaccurate. So when it comes to the applications, first of all, we have to normalize the data on the client side, because if you have a 1 pixel that is very small, like between 0 and 1, and 1 pixel that is very big, then the result going to be incorrect. The same problem that we had in the neural networks too, or in the machine learning, because you have to make sure that your data is pre-processed and normalized. Otherwise, one the feature will dominate the entire learning process. And also you have to vectorize. Again, the one single ciphertext gonna hold hundreds or thousands of values. We talked about it previous session too. And this makes the processing much faster. Then we have to manage the key. Private keys always stay with the client. The evaluation key can be sent to the cloud so they can do the rotation or relinearization that they need. This is that helper key that I just discussed some slides before. And now in the server side, the execution, the server receives the ciphertext and also the context and the algorithm. And now it starts to do some mathematical operations on it and never knows what is the secret key. So it's doing just a blind computation, and whenever the error is so big, it just doing bootstrapping. Finally, we have to verify what if the cloud actually gives us the result, but the result is wrong computation. We can check that with the concept that is called zero knowledge proofs. So homomorphic encryption can prove that the server performed the correct computation without ever telling the cloud what is the intermediate values. So white matter is clear because like if we have like medical results that are sent to the cloud and the cloud tells us something wrong, like a wrong diagnosis, so that's even worse. I mean, better not to have any diagnosis than having a wrong diagnosis. There are many applications that we talked about. Just a quick recap. One of them again is private credit card, credit score checking. So you don't want to send your transaction to a central hub for checking. Instead, you encrypt all the data, and that central bank checking the score in encrypted data. But even don't know what is the score, but just share the decrypted score back with you. Or we can have patient monitoring. Let's say you have some smart devices that are checking your health. So they can encrypt the data locally and then send the encrypted pulse data to the cloud. And then cloud do some processing and return you the result. But cloud learns nothing about your health. Let's also, if we have two companies that are sharing a supplier and they want to uh, get more information about their routes and also uh, supply chain visibility. So they cannot ask that supplier to share all the data with them because some of them are sensitive from the other client. So instead, they can encrypt those data and just gives you the intelligence that you need. If you have DNA that you want to share with the hospital that they can check for any diseases, you don't need to share your DNA genome, a DNA sequence. Instead, you can just encrypt it and then the hospital check it without ever learning anything about uh, some sensitive information related to you and the diseases that you have. So this opens a lot of roads for us, especially now we can do processing on untouchable data. If there are very sensitive data in the past, we couldn't send them to the cloud, but now it is possible. So that brings us a lot of advantages. And so we have a lot of, again, regulations that can be satisfied with homomorphic encryption and pave the way for uh, processing the data without any legal ban. Or if you have intellectual property, let's say you have an AI models and you don't want others to learn the weight of that model, you can just encrypt those weights so people don't learn about that and just process the data. The client get the result back, but they never learn what is the weight of the model. So in this case, also the cyber insurance can decrease because you know that your hospital or your healthcare companies has lowered the risk of breach, so they can pay less for the premiums of insurance. So there are a consortium called homomorphicencryption.org. Please check it out. There are companies like Microsoft, Intel, IBM, and other companies that have formed this consortium, basically just to create a universal language so the different libraries can work together seamlessly. So we can have the same language. And of course, this has a lot of impact. It paves the way for many other organizations to also implement this. There are some open source solutions like Zama and OpenMind that provide high-level API, uh, so that abstract actually the complexity, and you can easily work with them even without having an in-depth knowledge of the homomorphic encryption. OpenMind is another one that also provides that privacy preserving AI tools that actually combine homomorphic encryption with federated learning. So multiple hospitals can share their stuff with the central hub without ever any of them knowing what was the patient data that the other hospital used. IBM also has homomorphic encryption lib that you can look it up that support both BGV and CKKS. And there are some platforms actually that can do all this stuff for you too. So you don't need to worry about that technicality and also cryptography because they handle it for you. So here we talked in this session that homomorphic encryption is production ready, and the hardware is the next frontier. We can use FPGA or GPU acceleration or ASIC And also we have the CKKS, that is the king of the privacy for AI. And also we have the parameters or the context that we are sharing between client and the server, and how to manage the noise, because again, that can explode. So we have to control it. You can read also the Open Mind blog, that are very nice articles, and also Microsoft SEAL tutorials, or FHE.org. They have a community that you can learn more about the homomorphic encryption. Yeah, again, so homomorphic encryption paves the way for, instead of asking who can we trust to share our data with, we can say we don't need to trust anyone. But at the same time, I share my data with anyone that I like. So this is actually a very big deal, and this is something that's gonna help a lot for bringing a lot of possibility to life. Thank you so much for watching today. See you in the next session, and we probably talk about the mathematics of CKKS, and then we move on to the some Python programming for homomorphic encryption.